All right, so our next speaker is Sammy Sidhu. He's a senior engineer at a company called DeepScale, doing autonomous car stuff. His background is high-performance computing as well as deep learning to solve problems of perception for autonomous vehicles. Prior to DeepScale, Sammy was an AI researcher at Berkeley, working on high-frequency trading at 2 Sigma, and he interned at the applied machine learning team at Apple. So, Sammy?
Hello, everyone. So once again, I'm Sammy, and I'm going to be talking a lot more about training deep neural networks rather than just the architecture or essentially why they work. So a little bit first about my company, DeepScale. So we build perception systems for autonomous vehicles. And instead of us focusing on like the autonomous taxis like Waymo or Uber, we kind of focus on mass-produced vehicles, so getting self-driving technology into your car that you would drive to work. So your BMWs, Mercedes, all of those. We already work with a number of OEMs and suppliers, so a lot of tier ones. We also do a lot of open source. So there's a lot of neural network architectures that we've produced, and as well as software to train them at scale. If you want to know more, visit deepscale.ai. We're also hiring, so check that out if you're interested. All right, cool. So the overview of the talk is the following. At first, I'm going to talk about feature engineering, which is kind of the former state of the art, and contrasting that with learned features, which is kind of how convolutional neural networks or CNNs work. Next, I'll go a little bit in review of neural networks, just in case anyone missed kind of how they work. And then I'll be talking about the loss function or objective function that a neural network is targeting. Afterwards, I'm going to go into a little bit more optimization and how to optimize networks. And then I'm talking about data sets. And then finally ending with overfitting and underfitting. So let's get started. So as you see here, we have an image of a woman, and what we're trying to build is a face detector or maybe a face classifier. So to do this, what we end up doing is we end up creating features such as, okay, I'm going to build an eye detector. I'm going to build an eyebrow detector. I'm going to build a nose, mouth detector. And then from that, we could probably do some pose estimation or use these features to actually create a classifier for detecting who she is. And this is kind of how computer vision was done in the past, where you would hard code these features to do certain things. But as you can see, this looks like a very difficult task for anyone to start up. So feature engineering from computer vision can work well. Like, it just takes a lot of time and energy, right? To do this, you need both domain expertise. You kind of have to know, like, okay, how do I build a detector to detect an eye? So you have to know a lot about the eye. You have to know a lot about nose. You have to know about the convolution filters that would work well for detecting T on your forehead. And this requires both domain expertise and programming know-how. So you kind of have to be an expert in both. It also gets hard to generalize all cases. So for example, in that image, when you have a face looking straight forward, it's a lot easier than, let's say, if you had an angled face, or you had like worse lighting, or you had kind of like a sunset going on. And there's also a lot of variations of domain. So for example, what if your image works really well in the US, but it tends not to work that well in Asia or Africa, just based off of like maybe terrain or maybe different like features that a face would typically have in that area. So another way to get around this is to use generalized features, such as HOG, SIFT, HAR, any of those feature banks. But typically, since you're using a generalized feature set, the accuracy can really suffer. So let's look at the alternative. So this is DeepFace, which is from Facebook. And what this does is it classifies faces from raw images. So essentially what we have here is an image of a celebrity and then a label. And then essentially the features that make this label like get predicted and from the face, all those features are essentially learned throughout something we call training. So in the first picture, you see a face in the red. And as you go deeper, you see some things that you would typically see. So there's hot zones on the eyes, the lips. And as you go deeper, it becomes a lot more abstract. And it makes sense in a neural network. But to us, it may not make sense. So then because you're letting go of this kind of grasp of reality, and you're letting things happen in the dimensionality of a neural network, it can actually learn features that can be much more representative of your domain. So these learned features for computer vision can work extremely well. So in image classification, which I think the previous speaker mentioned, which is there's ImageNet, which is 1,000 classes, and you're trying to predict the which class is in an image. So before convolutional neural networks, the best was using SIF features and using a bunch of encoding on top of that, and the best result for that was 26.2% error, which is how many it got wrong in a top 5 prediction, which means it predicts something, it predicts top 5 things, and if it's the right ones inside of that, it's considered accurate. So before it was 26.2% error, and then currently the state of the art is a neural network called ResNet, which is from Microsoft, and it has 152 convolutional layers, and it has an error rate of 5.71%, which is really good. To train these neural networks, you only really need label data, deep learning expertise, and computing power, a lot of it. And training the network is essentially just learning features layer by layer until you can represent whatever space you're trying to represent. So the downsides of this is that because we're learning very abstract features where it may not make sense to us, it's really hard to perform validation. So if you have a picture and it's of a dog and it comes out as a cat, it's really hard to say exactly why that happened, besides just putting in samples and seeing what happens. There is no way to get a sense of why a neural network is predicting something the way it is. And it makes it difficult to validate. So just do a quick review of neural networks. We can see a neural network as a function approximation, which is kind of the way I view it, which is you have some equation, right? Y equals f sub w, which w is a set of weights that represents this function, and it takes in some x, which is the input. So in this case, right, when in our previous celebrity face detection, x is a 3D image, which is RGB, and x and y, and that's the input domain. And the output domain is probably like Kate Moss or some nice looking celebrity. And essentially what we're doing is we're finding a function that can map this input domain of an image to a label of who it is, right? And there is some perfect function out there that can do this. What we're trying to do is approximate that perfect function. And that's what neural networks are very good at. So by taking this input domain, weighing each input sample via a fully connected layer or a convolution, and then putting it through a nonlinear function, such as a sigmoid, hyperbolic tangent, or a ReLU, you can essentially have this perfect function that can approximate mapping from one domain into another domain. And I think that's kind of like the summary that I will go with throughout this presentation. Okay, so now, given a neural network, we have some input domain and some output domain. How do we essentially say what is a good function, right? And this is what we call the objective function or loss function, as it's called, right? So just because if we have like the same example we had previously, which is we have some celebrity face and we're trying to map to the name of the celebrity, a good objective is to minimize the error of predicting which celebrity it is, right? So, and let's do another example, which is the linear regression. The objective of linear regression is given data, we want to fit a line, which is y equals mx plus b, that minimizes the sum of squares of differences, which is called the Euclidean loss or L2 loss or R squared loss. And when we do linear regression, what we're trying to do is we're trying to minimize the distances of each data point from the line. So an example of a linear regression would be the following. We have some function. It takes in square footage and let's say median income in the area. And it predicts some value. And that value is the house value. And its value is mapped between 0 and infinity. So it's a very big domain. And what we would want to do is we have some loss function L. In this case, we're talking about the Euclidean loss. And we want to minimize this value. So find the best line that fits this. And that would look like this. You have a bunch of data points. You have a line go right in the middle. And what we're doing is we're finding the best line possible that minimizes the distance from the line to the data point. Right? And this is just called regression. And neural networks can also do regression just like this, but it doesn't necessarily have to be linear. you could use something like, I want to take in data about a bunch of stock market data and predict the price of an equity. And that could be a valid neural network regression, right? Another type of loss function is for classification. So what happens in the example where I do have a picture of a cat and a dog, and I want to say, given an image, what's the probability that it's a cat, and what's the probability it's a dog, right? And in the last presentation, they touched on this a little bit. And essentially, a softmax, I think, is a little bit overly complicated term. So essentially, what this really is just a logistic regression that has been normalized. And if you think about that, it's like, imagine you have, instead of having cat or dog, you have cat or no cat. You don't necessarily need 2 classes for that. All you really need is 1 class. All you need to do is take an image, do your normal regression, and then put in a function, like a sigmoid, which maps from -infinity to infinity, but maps that to 0 to 1. And the 0 to 1 value can be the output to perform your essential classification. So if it's above 50%, you know it's cat. If it's below, you know it's no cat. And essentially, every single class or every single output, like you see here, is essentially just predicting what it is. But the thing is, what happens in the case when you get dog 60% and cat 50%? Your total value is 110%. So in the case of this, where you can only really have one or the other, we would call this a disjoint probability set. So we would essentially want it to sum to 1. So what we do is we do a logistic regression to each one, which is essentially what a softmax is, and then sum them all up and then normalize. And with that, you go from a joint probability set to a disjoint probability set. But in the case where you can have dog and stray, they're not necessarily disjoint. So you wouldn't using a softmax doesn't make much sense. You can use a logistic regression for dog, and then a logistic regression to see how much the probability of it being a stray. So loss functions can be used for either classification or regression. There's actually more complicated loss functions, which we won't go into. But essentially, the goal is to pick a set of weights, which approximates this function, to make this loss value as small as possible. And it's very crucial to pick the right one. So for example, we talked about a regression being some predictor that goes from 0 to some range, or some range to some range. So you can have a regressor that goes from -100 to +300, and that's fine. So technically, you could use a regressor, like a L2 loss regressor, to predict probability. It would technically work. It just would be really bad, and you wouldn't want to do that. You would essentially want to use something that makes more sense. So when you do have this log loss, it does map from 0 to 1, and it actually makes the neural network keep a lot more momentum when it's going towards predicting, going from that 0.9% accuracy, like 90% accuracy, to like that 99% accuracy, when in regression, that is not that big of a distance. Cool. So just to summarize, loss functions are essentially what you're targeting as the objective of your neural network. And it can be, I think it's probably the most important concept in AI. Because, I mean, if you always talk about the sentient AIs, what they always say is that, like, if I tell a AI, say, oh yeah, so, cure cancer, one of the things it might do is say, oh yeah, I'll just kill all humans, therefore cancer will be gone, right? So it's kind of crucial to pick the right objective function, because that's essentially what your network is moving towards. All right, cool. So now that we have our loss function and neural network, how do we know what part of the neural network is responsible for causing the error? So I guess I'll give a little bit more intuition on this. So if given a neural network with tons of weights, and you have layer by layer, and initially what we do is we just randomize this. We just give everything kind of like a random weight from a Gaussian, and we say, all right, cool. I'm going to put in this image, and I want to see how bad this image is. So it goes through, and it says it's Kate Moss when it was actually like Brad Pitt, right? And that's pretty different. And we want to say, all right, cool. Where is this coming from? Like, what part of the network is responsible for thinking Kate Moss is Brad Pitt? And this is essentially how we improve our neural network with training. So I'm going to go back to the simple linear regression as an example, but this extends very nicely into multi-layered nonlinear neural networks. Okay. So let's define our loss function. And one I've been talking a lot for regression is the Euclidean loss, or L2 loss. So we're going to find the loss function as L. And L is equal to 1/2 y, which is the label, what we're predicting, so the value we're predicting, minus y hat, which is the value that actually comes out of our function. So y is the truth, and y hat is the value we're predicting. We get this difference and we square it. And that is our loss for any given prediction. So what we want to do now is we want to talk about how y hat, which is the value we predict out of our function, how this contributes to the loss, right? And if you think about how we think about contribution, we can think about a derivative, which is how does one affect the other given some point. And derivatives work really well in this area. So what we say is that dl, which is the change in loss, how it's affected by dy hat, which is the function that outputs our prediction, we take the derivative and we use the power rule and whatnot, and we take the delta of y hat, and what we end up getting is we get y hat minus y, right? And that's the derivative of how the output of our linear regression affects the loss. So if we're fitting a line, we know that y hat should equal mx plus b, where m is the slope and b is the bias. So it's just a simple line like we showed earlier. And we have two ways to optimize. So instead of having millions of parameters, we only have two parameters in this case. One is slope, the other is bias, which is m and b respectively. And then now we can also think, okay, how does the output of a linear regression get affected by slope? And we just take the derivative respective to m, and we get x. And we also think, how does the output of our linear regression get affected by the bias? And that's just 1. We're just taking the derivative respective to b. Okay. So now, given a data set that looks like this, which is a simple line with some Gaussian noise, what we can do is the following. Given our loss function, which is kind of, which was the L2 loss, what we can do is, given the data set and the noise we have in that, we can actually compute what the surface of the loss looks like. So one of the axes is y, the y-intercept, and one of the axes is the slope. And given these two, we can actually print the contour. And it's easy to see in our domain that what we want to do is see the m and b, or slope and bias, that we get to the bottom of the surface, right? But when you have something with a lot higher dimensionality, you can't visualize and say, oh, there it is. So what we end up doing is the following. We pick two random parameters. And let's say in this case, we pick -2, -2, which is in the far right corner, that top red point. And in this top red point, what we're trying to do is get to the bottom. So what we can actually do is use those two handy derivatives we had earlier. And a derivative gives you slope, right? It gives you the direction of what the contour is going. So because if we know where the contour is going with the slope and where the contour is going with the bias, right, what we can do is actually use those two derivatives together in a vector. And that will give us direction and like a magnitude, right? And this vector of two derivatives is called a gradient. And when people talk about gradients, that's what they're talking about. They're talking about a set of a vector or even a matrix of derivatives respective to every parameter. And with this, you can actually know where down is. So what you can do is you can actually walk down the surface. So you start from the red, you compute the gradient in both directions. You can compute the gradient and you actually take a step. You take another sample and you take another step. And you can repeat this until you get to the very floor of your surface. So if we know that dl over dy hat, which is how the linear regressor contributes to the error of our loss function, and we know how our loss function gets outputted respective to our slope and bias, we can use the chain rule, which is from calculus to actually figure out how our slope contributes directly to our loss, and also how our bias contributes directly to our loss. So we can just chain these together, and the dy hats cancel, and what we end up getting is dl over dm, and dl over db, which is how the loss is affected by both slope and bias. And using these two gradients, or two derivatives in a vector, we actually get the gradient. So to make any update, what we do is we just make our weights this. We do m, which is the slope, equals m of the previous iteration, plus some constant times the derivative. So what we're doing is we're getting the direction where down is and slowly adding it to our actual weight. And when we repeat this, we will eventually converge to what the lowest is for m and b. And this alpha parameter, this constant I spoke about, is called the learning rate, which is how fast we want the network to learn. If it's too big, you might just overshoot the minimum. And if it's too small, it would just take forever to get there. Okay, so remember, the idea is we want to just walk down the surface until we get to the bottom. And the more lower we get, the less loss we have, and the more accurate it becomes. So this is how it kind of looks like, which is pretty cool. So as time is going on, it's learning both the B and M. So it looks like the initial guess for B was pretty good, but M takes some time to learn. So as time is going on, it's actually getting more and more accurate because it's walking down a gradient and actually getting to the lower part of it. And it's just doing this per update. And it's actually getting to what it actually should be. Okay, so this process is called gradient descent. We're starting from some random point in the gradient of the loss, and we're descending using gradient updates. And then if we constantly repeat this, we will get to the minimum. So this gradient descent is not just limited to linear regression. We can use it for very deep, 150 layer, 1,000 layer deep networks. The concept is the same. We can take derivatives respective to any parameter in the network. So if you have a weight in the first layer, you can take the derivative of the loss of the whole network respective to some parameter in the first layer. And this concept of taking derivatives respective to parameter also works if you're talking about convolutions. If I'm talking about a convolutional neural network, I can take derivatives respective of the loss to some convolutional kernel, which is kind of interesting. And to avoid this math complexity and recomputation, we can actually just use a chain rule again. So what we can do is, for every single layer, what we do is take the derivative of the output of that layer to the layer before. So we start off in the back, take the loss to the derivative of the loss to layer n-1, and then n-1 respective to n-2. And we can chain this all the way back. So if we want to find the derivative of the loss to any layer, we can actually just chain it going all the way backwards. And this process is called backpropagation. So we essentially start from the image, we do our convolutions, our fully connecteds, we do whatever we have in our network, and we get to the end, which is a singular loss value. We get to the loss value, and compute it to the layer before, and compute that to the layer before. So you see that every single node in the network has both its value and its derivative, which is denoted by lowercase delta. And what we can do is, because of this, we can compute the gradient with respect to every parameter in a single pass. And once we have the derivative with respect to every parameter, we just do our update. We just update the thing, and the network is a little bit better. And this is called backpropagation. So typically, the terminology you would typically use is you have a forward pass and then a backward pass. Forward pass is doing the inference. So if you have some deployed network, you would only do the forward pass or inference. When you're training, you do forward pass and backwards pass. Okay, so given the fact that we now have gradients, the weights, what's the best way to apply these updates? So in the linear regression example, what we did was we grabbed a random sample from a data set, and we computed the gradient, and we applied it to slope and bias. We repeat this until it converges, and this process of just grabbing samples, updating until we're good, is known as stochastic gradient descent. But is there a better way to do this? So essentially this process of finding the best possible set of weights to minimize the loss for our objective, this is called optimization. And essentially what we're doing here is just trying to optimize these set of weights. So typically when you have the linear regression, you wouldn't really do it the way I'm talking about because there is a closed form solution called least squares. But for the case of neural networks, you have this very non-convex contour, which has tons of valleys, has saddle points, and all that. So there is not really a closed form solution to this besides just computing and then applying updates to get there. So now we're going to talk about what are some better ways of doing this painful process. So one is called momentum. And when you're doing good, you kind of build momentum sometimes, and you can move faster to your goal. This applies very much in deep learning networks as well. So what we can do is that we can keep a running average of our previous updates and add that to our current update. So I'll clarify a little bit more. So these surfaces you see here are contours of the loss function. So you can think of it as a projection onto a 2D plane of the loss surface. And every time we grab a sample, it kind of makes us learn a little bit better, but it may not be like a pure sample that would take us straight into the middle, which is the global loss. So what ends up happening without momentum is that we ping pong, but we have a slight horizontal velocity. And we eventually will get to our goal, but it takes a lot of updates. So the thing is, if we keep a running average of our both speed and direction, what the horizontal, the vertical aspects of this can actually cancel out. And we actually have a way to move towards our global minimum in less updates because we do have this momentum that is saying to go towards the middle. There are also other optimizers besides stochastic gradient descent, or SGD for short. One of them, some of them are called AdaGrad, AdaProp, or MSProp, Atom. And to be honest, like they're pretty much almost all the same, except the way that they tune learning rates and some parameters are just a little bit different. So some use root mean square to determine what the learning rate should be. Some use other methods. And essentially what they all do is they tune the learning rate, which is how big your steps are to reach your global minimum. So in stochastic gradient descent, you would essentially fix your learning rate to whatever you think would be correct. And as a network or train, you would cut it yourself or tune it yourself, and you would do that by hand. These ones kind of do that automatically. So in the beginning, when the answer is really obvious of where you should go, like where I'm moving towards the middle, it can kind of make a big learning rate, so it takes bigger steps. And as time goes on, it can take smaller steps to fine tune. Typically, if you do with SGD, it takes some practice and some intuition to get it right. And these are great for fast convergence when you're prototyping. Like if you're just trying to test out a network architecture, you can give it one of these optimizers, and you typically do pretty well. But it is pretty finicky for reaching its lowest loss possible when you are dealing with very complex networks. So when you do these 1,000-layer or 100-layer networks, these optimizers don't work as well because you need something a little bit more stable. And we can actually visualize how they work. So you see that SGD can actually get stuck on this point right here, and this contour of the loss is something known as a saddle point. So this SGD can actually get stuck here while these other functions that can actually take bigger steps or smaller steps can actually get out of this valley and move down. So you can see that even with momentum, SGD with momentum can get out of it. And these other ones just kind of accelerate as time goes on. So I'll play one more time. But essentially, they can tune how fast they move just based off the momentum they've had before. Okay. But essentially, I would say the hardest part about training these networks is actually optimizing them. It's very difficult, and it takes a lot of time to build that intuition. Okay. And I would say the second hardest part about neural networks is the actual data sets. So I'll define a data set a little bit better. So a data set is essentially the set of data points that you actually train on. So in the example before, if we have celebrity faces, you would have a picture of Kate Moss saying it's Kate Moss, and you have Brad Pitt saying it's Brad Pitt. Or in a case of an animal classifier, you would have a picture of a cat and say it's a cat, and a picture of a dog and say it's a dog. And essentially, you want a diverse enough data set that's large enough to train your network without overfitting. And overfitting essentially is just memorizing the data set, and we'll go a little bit more into this later. So you want to diversify my data set. So if you have, in the case of the cat and dog example, you have like 99% pictures of cats, what your neural network might do is just say, hey, everything's a cat. And in your network, you could technically say you have 99% accuracy, which is technically true, but it's not very good. One thing you can also do with your data sets is augmentation. So in the example of ImageNet, or when you're training something to classify faces, symmetry is something that makes sense. So if I have an image of me right now, and what I can end up doing is I can actually flip my image in the vertical direction. So it actually flips the other way around. So I'm kind of mirrored. And to a network, this still makes sense as a face of Sammy Sidhu. But in the case of flipping it the other way around, so I'm upside down, that's not really what a face looks like. So it doesn't make sense. So you can actually augment your data to essentially generate more samples. So in this case, we would have twice as many samples. We can also add rotation. So I can slightly rotate my image, because essentially you can't always assume that someone will be directly in the middle, perfect pose. You can actually do some rotation and do a crop to get a slightly augmented image. You can also add noise, hue, contrast, and this makes your network a lot more robust when you train. It's essentially having a lot bigger of a data set. And this augmentation is essentially very useful when you have the case of rare samples. So if you did have that 99% samples of dogs and only 1% of cats, what you can end up doing is you can just generate a lot more samples of cats given what you have already. So I will go over the common data sets that you'll use or you see in a typical vision application of neural networks. So the first is called MNIST, right? And it's essentially from the postal office in the 90s. And essentially it's 6,000 images and it has 10 classes. And a class is defined by like what an output could be. It could be from 0 to 9. And this is essentially the hello world of neural networks. So this is typically the first example you'll ever do if you do end up playing with any kind of training framework. It works really well, and it's essentially a solved problem. But it's always great to, if you're first testing out a network or some new architecture, it's generally good to just test it on MNIST, because if you don't get 100% or 99% accuracy with your current network, it may not generalize well for whatever application you're doing. The next one's called CFAR. And it's 10 classes of images, very low resolution. And I believe there's 60,000 other images for this one as well. And this is kind of a little bit more a step up from MNIST. And typically a convolutional network with a few layers can do pretty well on this. And this is typically a little bit easier to train too. So it takes, MNIST only takes maybe a few seconds to train or a few minutes to train. While this one may take, if you have like a commodity computer, maybe like an hour, a couple hours. So it's relatively simple to train. And the next one's kind of like the behemoth that everyone talks about, which is called ImageNet. So ImageNet has 1,000 different classes, and some of them are very similar. So for example, some of them are different species of birds, which humans can't even get right. So it's typically very challenging. And this is kind of the competition that every year that everyone talks about. So the best result for this is 5.7%, and that's from Microsoft ResNet. But typically when you see results from ImageNet, you know that it was pretty challenging, because I remember when I was doing deep learning research, and we had some high-end GPUs, it would take 3 to 4 weeks to train on ImageNet. Today it's a lot smaller. You can train ImageNet within a couple of days now using clusters, but back then you would do an experiment, it would take 3 weeks, and it was terrible. All right, cool. So now we talked about data sets and neural networks. Let's talk about overfitting and underfitting. So in a very short way of saying it, what is overfitting? And it's essentially just fitting to the training data, but not generalizing well. So the best way I think about this is kind of like a story from me in kindergarten, where I was in a class when we read this short story every day. And since we read it every day, there was one kid who couldn't read, but he pretended like he did. because he ended up just memorizing the book because we read it every day. So then one day, my teacher was like, I'm calling his bluff. So she made us read it backwards. And this kid was just screwed. So that's essentially overfitting. This kid had just memorized the sequence of words going in order. But when it came to the testing phase, he did not do very well. So that's kind of like overfitting, when you just essentially memorize the data set and output what you want to see, what the person wants to see. Because essentially, in the end, we're just minimizing our objective or loss function. What is underfitting? Underfitting is essentially when our model does not capture the underlying trends of data, which just means poor performance. Now, how do we tell for each one? So first, let's kind of visualize what they look like. So you see this set of data points it has a slight curve. It might be a parabola. And underfitting will essentially be trying to fit a linear function into that. And yeah, it kind of captures it, but there's missing trends in that. There's no upward curve and maybe some other parameters in there that gives it some higher polynomial. But it's not really capturing the other trends. And the right side, where you have overfitting, we're kind of just fitting a lot of squiggles, and we're kind of just memorizing each data point. So yeah, if we do our loss function on here, it will be very good. But when it comes to generalizing for a case that's never seen before, it's going to do really poorly. So in a case that's never seen before, both underfitting and overfitting will give you bad results. But the balanced one in the middle, which is not quite underfitted, but not quite overfitted, will give you the best results when it comes to actually applying your model. So how do we figure out what's happening? In this case, we can plot it and actually see. But in the case of neural networks, you can't plot your whole data set and see why it's happening. It's too highly dimensional. What we can do is this. We split our training data into 3 different parts. We call one the training set, one the validation set, and one the training test set. So we split it into 3 parts. During training, here's what we do. We learn reading the training set, so we pluck samples from the training set and do our gradient updates. And after we go through the data, the whole data set once, which we define as an epoch or epoch, depending on how you pronounce it, what we do is we evaluate our model using a validation set. So the validation set is something it's never seen before, but after it's not in the training set. So we essentially evaluate our model using data that the network was not trained on. Okay, so we repeat this. And after we're done training, what we can do is we can actually use the test set to see how good our model really is on data it's never seen before or has never been validated on before. And this is kind of important because of this. What happens in the case where I'm constantly tuning my model, and I'm tuning my model so that my validation loss gets better? There might be a chance that I'm actually just optimizing my model to fit the validation set better. That's still some kind of overfitting, but that's me overfitting. The thing is, we want something else where we can actually just test our whole model as a whole on data that's never seen before. And typically, if you do end up doing Kaggle or whatever, the test set is never released. And the test set sometimes has restrictions like you can only do 1 submission per day. That's actually one of the reasons why Baidu got kicked out of ImageNet, is because they constantly submitted with different accounts to ImageNet. And that was so they can get different results for how the test set performed on whatever model. They got banned for the year. So it's kind of funny. So essentially, how do you know when you're overfitting then? So the red line represents the training accuracy. So the higher is better in this case. So this is the accuracy. So the red represents training accuracy. And typically, as you're training and your model gets better on the training set, which is data it's seen, your validation set should follow. Like, as you get better at predicting the training set, validation should get better as well. But what happens in this case, you start memorizing your training set, and you start just remembering the samples that you've seen before. That's where you get from the blue line. The blue line essentially is your model is so fit to the training set that it kind of doesn't really know what to do when it comes to validation. So to reiterate, training loss is low, and validation and test loss are going to be high, because essentially just memorizing what the training data is. So how do we combat this? One thing is we get more data. More data is usually better. and we can see more samples and actually perform better. One is data augmentation. We can augment the data more, put in rotations, add more noise, and this makes the model a lot more robust. We can do regularization. So one is called weight decay, and what we can do is we can actually get all the parameters in the network and find the magnitude of them and add that as a loss function. What this means is that what I'm telling the network is, hey, if you rely too heavily on any one feature, you get penalized. So then it actually optimizes to rely less on any one feature, and because of that, it becomes a lot more robust. You're essentially punishing it for relying too much on one thing. And another thing you do is you can actually do something called dropout, which is I compute the gradients, and let's say I ignore half of them and I apply it. Essentially what this does is makes the network a lot more robust because it learns different ways to come up with any one result. It wants to minimize its loss. And if you're ignoring half the things that it tells you to update, it will find other ways to make itself a lot more robust. And lastly, you can just have a simpler model. If you're having like a 20-layer network for MNIST, then that's probably wrong. So you would want to use a simpler model for that. Simpler model typically means you can generalize a little bit better. But if it's too simple, then you don't capture the underlying trends. So you want to be in the sweet spot between underfitting and overfitting. That's kind of the goal. Okay, now how do we know when we're underfitting? So the training loss would drop a bit, and then it kind of stops. It kind of just goes down a little bit, and it kind of just plateaus. The loss is still high, and it's still plateaued. And the training loss and validation loss are pretty much equal. So when they're both kind of equal and your model just kind of plateaus a bit, it typically means that your model is not complex enough to capture all the trends of the data. So one thing you can do is just make a more complicated model. And when making a more complicated model, it can actually learn more about the underlying features. Another thing is that your regularization might be too high. If you're like dropping out 90% of your parameters, then your model will never learn anything. If you also penalize if it relies on anything, then the model will not learn anything because its goal is just to minimize the loss. All right, cool. So the key takeaways. Neural networks are function approximators, and they're pretty good at it. Deep learning can work surprisingly well, as we learned from image classification, and it also it does really well in other domains like speech, machine translation, self-driving cars. It works really well for a lot of it. Optimizing these networks is more of an art than a science, and it requires time to develop the intuition to make them work. Making a good data set is very hard. Typically, if you just train on pre-provided data sets, they're pretty good, like ImageNet or CFAR or MNIST. But making your own data sets that work well is a very difficult task. Overfitting is something that makes it very hard for applications. So if I overfit and I have amazing training loss on my data set, if I deploy that in the wild, it might not work so well because it's not robust for that. And we can find how robust our models are and see how much we're overfitted by doing something called validation testing. And that's splitting a data set into parts and actually seeing how it performs. All right, thank you. I guess we'll do questions now.
Excellent, excellent. So yeah, we have if you have a question, we have a microphone right here.
Hi, you didn't mention anything about simulated annealing. Is that gone out of style, or is that still in use?
So simulated annealing still has its uses, but in a little bit of a different way. So as I mentioned before about these optimizers, what you end up doing is as time goes on, this learning rate parameter that we talked about gets annealed. And let's see, where was it? These optimizers actually do the simulating on themselves. So essentially, when you have stochastic gradient descent, what you end up do is you pick a learning rate, and as time goes on, you end up getting stuck in a valley, or you're not lowering your loss anymore. What you can end up do is you can actually lower your learning rate, so you can actually go down. So simulating is still used, but it's typically only using the learning rate parameter. All right, any more questions?
Hi. I think that today's the training, those guidelines are very good for practical training. So, but I was wondering if you can say something more about what's different in training a deep neural network, because those are for traditional learning. Those are very good, you know.
Okay, so especially just for deeper neural networks? Okay. So typically training with deep neural networks, what we want to do is typically want to use stochastic gradient descent. You want to start with a learning rate that you know will converge. So what you end up doing is training these deep networks. There's a lot of, I guess, complexities in the gradients. So what you end up doing is you can actually start with a parameter like 0.001 alpha rate. And as you start going down, you typically will plateau early. But that doesn't mean that's where your network has converged. What you can end up doing is you can actually just keep on cutting it, so a factor by 10, which is typically common. So you set it to 0.01, and say every, 10 times I go through the data, I cut it by a factor of 10. And for most deep networks, that actually works surprisingly well. Besides having good data and all of that, they're actually not too hard to train when you talk about the traditional data set.
Hi, Andy Goff from Microwork. I wonder if you could tell us a bit more about what makes a really great training data set. What about maybe about variety and the size of the data set as well, and what sort of trade-offs you have to make and what sort of performance you might expect?
Okay. So typically, the more data we have, the better, right? But of course, it's not for free. Training these networks is very complicated. It takes a lot of compute. So typically, you don't want to have data sets that are like infinitely sized. So what makes a good data set is when you do have variety in the data set when it comes to just end-to-end learning. So in the case of something like, here's like a story. So typically one time with Google, with self-driving car, it saw some lady in like a wheelchair like whacking an umbrella in the street. And the car just stopped because it literally did not know what to do, right? So of course, you can't really capture that in your training set because that's so random, right? But what you can do is you can actually add noise to your data set such that it would perform a better action. So in this case, what you can end up doing is maybe you could simulate road debris in your data set, and you can actually make that more robust. You can actually simulate lesser things and not actually have to collect data on everything, if that kind of makes sense. But what typically with size, there are rules of thumb when it comes to the number of parameters in the network and how many samples you would typically want. And I think the rule is like you would want one sample for like every parameter you would have.
Okay, thanks.
So balance, right?
Mm-hmm.
So my name is Sammy from Intervac, and I just have a question about adding additional labels to your training data. So obviously you won't be able to capture all the different types of objects that are out there in this data set, but if you wanted to add to it, is there a preferred way to do that? Or
Yeah, there is. So that's a very good question. So let's say in the case where we have, we're classifying 10 different faces, and you want to add an 11th. Is that kind of what you're asking?
Yeah.
Okay, so the thing is, if we train on a huge data set of 10 different faces, and suddenly we add an 11th face, like retraining the whole data set and spending hours doing that is so not worth it. So what you can end up doing is you can actually freeze the whole network, except the last layer. So if you think about any neural network, it's essentially just a feature extractor and then like a logistic regression or a linear regression in the end on those previous features. So what we can do is we can actually freeze all of the weights in the network except the last layer, add an additional node, and just retrain that last layer.
Okay.
And that's typically, it's called transfer learning. And that's typically how you would do it.
And another question, if I could. Is it possible to generalize ImageNet, because it contains color data, basically, the RGB images, but is it possible to generalize that to monochrome grayscale images, and what kind of accuracy loss would you get with that?
It has been done. So there is an architecture called VGG19, which is a 19-layer convolutional net. And it does have a grayscale component to it. And from what I remember, it's only a few percent error additional. It still works pretty well. Mostly it's the texture that gives you the most amount of data or most amount of information when you do this image classification.
Interesting, thank you.
No problem.
Michael Hubrick from Cadence. I have a high-level question. So when you describe kind of the evolution of this, of the convolutional networks and how image processing was done in the past, so the point of critique of the past was essentially the expertise required to build these algorithms and models and all that. But on the other hand, if I take what is really required to train a network, so the training it well and finding the right data set seemed to be pretty difficult, pretty artsy, pretty non-intuitive, right? And so kind of my challenge question is, to what extent do we know that we really made progress? Especially in light of the fact that the computational cost of convolutional networks is pretty high.
Could you repeat the question, that last part of the question?
The computational cost of convolutional networks compared to histogram gradients is pretty high cost in general. I mean, it depends on the network, but usually we're talking about very high compute.
Yes. So typically, if you do normalize accuracy over the number of flops it takes, I do believe that the older previous like SIFT or HOG or HAR is going to be a lot better. And you do have a lot more hardware optimized for that just because it's been over time. So I would say yes for these networks, because you're literally just kind of brute forcing what the best filter banks are, the best compute is. It does take a necessarily amount of really high amount of compute. We're talking about hardware that does 12 teraflops per second. Typically, when we talk about like NVIDIA, or these networks can take gigaflops per image, which is kind of ridiculous sometimes. But just based on current hardware, it's not that much of a concern as it used to be.
Okay, thanks.
The difference between a training set, validation set, and then the test set seems to be an important relationship, especially if you get into competitive arenas, of which automated vehicles seems to be one that's coming along. Mm-hmm. What's your sense of the degree to which the oversight, whether it's through government or insurance company, will be able to keep up and both create that kind of test set and keep it secret enough that there's no cheating?
Okay, so that's a very good question as well. So that's a good point, because essentially, let me present one way of doing the split. So let's say I have an hour of data, right? Or let's make it bigger. Let's say I have 100 hours of data. And let's say I have 10 frames per second. Right, so I have 100 hours of data at 10 frames per second. Technically, what I can do is I can just shuffle all the data and take half of it for the test set and half of it for the training set. So technically, I have disjoint training and test set. But if you think about it, given the probability of sampling at random, it's going to be interleaved, right? You're going to have 1/10 of a second on the highway, and then the other 10th of seconds of me in the test set, and then you're back in training on the highway. So in reality, it's just training on 5 seconds or 5 hertz in training and 5 hertz in the test set. And of course it's going to do well, right? So I mean, if you say to government, yeah, we have a disjoint test set on highway driving data, then of course that's sketch. But in the case where you say, okay, cool, we have the first 50 hours is training, and the next 50 hours is a test set. It's technically the same amount of samples, and they both are disjoint, but it's a lot more of an effective way of testing.
I was wondering if you have any experience for training with pruning in mind. I mean, you hear for inference that like mixed precision is coming, and pruning is going to improve compute per cost or power. So if you have pruning in mind, does it change the big picture of what you're discussing with us?
If you're training with pruning in mind, so it's kind of I guess a difficult question to answer, because it's kind of like the same thing with quantization, right? So pruning is essentially when you do train a network, you find what filters are relevant, and then the ones that are not, you can kind of remove it from the picture. And the thing is, until you train the network, you won't really know what's relevant and what's not relevant, right? One thing you kind of can do is you can train a network and prune it and see, okay, given each layer, how many filters were actually relevant, right? How many weights were actually relevant and how many were just kind of near zero and didn't really matter. So given that, you can kind of see what's the amount, the max information gain per layer. And the next time you train it around, you can actually use that information to make your training go a lot smoother and a lot faster. Right. All right, thank you.
Any more questions? All right, thanks, Sammy.